Good afternoon, my dear students. My name is Dr. KCH Apparao, working as a Associate Professor in Mechanical Department, Institute of Aeronautical Engineering, Hyderabad. Okay, in previous class, we discussed what is the importance of heat exchangers and classifications of the heat exchangers also we discussed in previous class. And applications of heat exchanger also is now we'll see the design of heat exchangers. So there are four methods to design the heat exchangers. One is the LMTD method, LMTD, log mean temperature difference method for the parallel flow and counter flow. So two methods. So next one is the NTU method for the parallel flow and counter flow. So totally, so there are four methods or two methods and four derivations for the design of heat exchangers. First of all, we will see the LMTD method, log mean temperature difference method. Okay. So first of all, we will see the LMTD method for the parallel heat exchanger. Now, next we will see the LMTD method for the counter flow heat exchanger. Okay, we will see the first of all LMTD method for the parallel flow heat exchanger. Before going to that, just we'll see what is LMTD. Okay, so you know that in heat exchanger, just like suppose this is the inner pipe, and so this is the outer pipe like this one. Okay, so flow is like this one. Because hot fluid inlet, hot fluid outlet. So cold fluid inlet and cold fluid outlet. So in which just like flow is like this one. Here just like the temperature is varies from the one side. So side A to side B. It means so temperature of the hot fluids gradually decreases and the temperature of the cool fluid is gradually increases. So at particular time from point to point the temperature ranges will be decreases. So the temperatures will be decreased. So we have to consider the logarithmic mean temperature difference for that one. So just like so that is we'll see this one. So it means so logarithmic mean temperature difference. So you know that the temperature difference between the hot and cold fluid in the heat exchanger. So it varies from the point to point. So in addition to various modes of heat transfer, because here we will see the conduction and convection also. Okay, so therefore based upon the concept of just like appropriate mean temperature differences, so we can call it logarithmic mean temperature difference. So we can calculate the rate of heat transfer, total heat transfer rate in the heat exchangers. We can express like this one. So this is the Q. You know that rate of heat transfer is equal to UE into delta T LM. So this delta T LM is nothing but logarithmic mean temperature difference. Okay. So how to find out here logarithmic mean temperature difference, and we know the U is the overall heat transfer coefficient and the A is the area. Okay. So in this method you have to find out the LMTD, logarithmic mean temperature difference, for the parallel flow and the counter flow. Okay. So first of all you will see the how to find out this logarithmic mean temperature difference in parallel flow, and how to find out the rate of heat transfer for the parallel flow heat exchangers. we'll see. Okay, so this LMTD method, it involves the some parameters like inlet and outlet temperatures of the fluids. So two fluids we'll see. One is the hot fluid, another one is the cold fluid. So here in this method also, in heat exchangers only, heat transfer takes place from the hot fluid to cold fluid. Only heat transfer between two fluids only. Okay. So you'll see the inlet and outlet temperatures of the hot fluid and cold fluids, and overall heat transfer coefficient. So this is also uh, involving parameter in this LMTD method, and the total surface area. So A, so U and area and the temperature, cold fluid and the hot fluid inlet temperatures, and cold fluid outlet and hot fluid outlet. So next one is the just like rate of heat transfer. So Q. So these are the important two parameters which are involved in this LMTD method. Okay. So we can say the final formula is equal to, already noted that UA into delta TLM. So delta TLM is the just like summation of just like combination of the inlet and outlet temperatures of the fluids. Okay. So here just like one more very important and noted point is that, so since hot fluid is transferring a part of its energy, because heat transfer takes place from the hot fluid to cold fluid. So hot fluid is transferring a part of its energy to cold fluid. So there will be an increase in enthalpy in the cold fluid and a corresponding decrease in the enthalpy of hot fluid, because hot fluid is losing heat and cold fluid gains the heat. So the enthalpy of the hot fluid will be decreased, and the enthalpy of the cold fluid will be increases. Based upon this one, this is the formulas. You know that these are the energy formulas, energy equations according to thermodynamics. You know that one. So Q is equal to mH and CH. So hot fluid mass flow rate of the hot fluid and the specific heat. So we can say capital CH. So mHCH into hot fluid inlet. So hot fluid inlet minus hot fluid outlet. Okay. So hot fluid temperature differences. You know these formulas. Otherwise you can read it like this one, capital CH into THA minus TH naught. So these are the energy equations. You know that. So similar way. So Q is equal to, for the cold fluid, MC, so cold fluid mass flow rate into specific heat of the cold fluid into temperature differences. So Tc naught is always greater than the Tc. So the temperature difference of cold fluid is, so Tc naught minus Tc. Okay, so these are the energy formulas. We have to consider this one. So in this LMTD method also. So next up, we denote the difference between the hot and cold fluid. So delta T, we can denote that. So hot fluid temperature minus cold fluid temperature. So delta T is nothing but, so hot fluid temperature minus cold fluid temperature. So then you know the formula, actual rate of heat transfer is equal to UA into delta TLM. So delta TLM is nothing but so logarithmic mean temperature differences across the heat exchangers. So this value will be varied to parallel flow and the counter flow. So okay, we'll see the derivation of LMTD method for the parallel flow. So we know that first of all we will see the just designing of our construction of the we will see first of all what is parallel flow. You know that parallel flow, suppose this is the inner pipe. So this one is the outer pipe envelope. So heat is flowing like this one. This is, it shows the just like so through inner pipe hot heat flow just like a hot fluid is flowing, THA minus, this is the TH naught. Okay. The direction of hot fluid also just you can see from left to right. Here just like cold fluid, TCA is the entering like this one, flowing like this one, envelope. So this one is the TC naught. Okay. So here just like both the fluids flow in the same direction and parallel to each other. So we know that that is called a parallel fluid exchanger. We can consider this is the parallel fluid exchanger because the fluids like cold fluid and hot fluid is flowing in the same direction and parallel to each other. So you know that this is the parallel fluid exchanger. Just like we can just draw a temperature graphs also. We already discussed it in previous class how to draw the temperature graph for the parallel fluid exchanger. So this one is the parallel fluid exchanger. You know that. So hot fluid, so inner pipe and envelope outer pipe. Okay. So envelope pipe is covered with the outer pipe. Okay, heat transfer takes place from the hot fluid to cold fluid through the inner surface of the or just like surface of the inner pipe. Okay, this is the hot fluid inlet. This one is the hot fluid outlet. Okay. So next, so this one is the cold fluid inlet and this one is the cold fluid outlet. So both are in the same direction and parallel to each other. So this is the parallel fluid exchanger. So the temperature graph is like this one, you know that one. So here if you observe this one, this is the just like NDA and NB. So NA, so this is the A portion, this is the B portion. Here just like cold fluid inlet and hot fluid inlet in the same enters at one end, same end. So cold fluid inlet and hot fluid inlet. So you know the temperature difference between the cold fluid and hot fluid is very high. So we can show that one that delta T1 is nothing but hot fluid inlet minus cold fluid inlet. Okay. So here in case of hot fluid, temperature is decreasing order because hot fluid loses the heat, and cold fluid, if you observe that graph, so cold fluid temperature is gradually increasing. It means so heat is transferring from the hot fluid to cold fluid. So if you observe this one, for a point to point, the temperature values of the temperature, the range of the temperature is varying. So here just like at the B point, it means here. So hot fluid outlet and cold fluid outlet we can see at the B section. So end of the another section. So it means B. Okay, here this is the cold fluid outlet. This one is the hot fluid outlet. So the difference between the cold fluid outlet and hot fluid outlet minus cold fluid outlet, it is represented by delta T2. It means delta T2 is equal to TH0 minus TC0. Okay. So here is just like in between. We'll see that one later. Okay. So for the derivation of any equation, you know that initially we will take small elemental area and derive the formula and integrate that one, then we will get the final formula. So here also just like takes a small elemental area. So DA. Okay. So this small elemental area. So we can represent this one DA. Okay. The corresponding temperatures for the small elemental area, you can see that is the, so here just like temperature is gradually decreasing. So this is the DTH. So here temperature is gradually increasing, that is the DTC. So temperature of the cold fluid, temperature of the hot fluid. So delta T shows the TH minus TC. So here just like same diagram you can see like this one. Mainly this type of cold fluid is mainly used for the oil coolers and oil heaters and water heaters, just like. Okay, this is the parallel fluid exchanger. So here you can see the just like graph of the parallel fluid exchanger. So delta T1 shows the hot fluid and cold, hot fluid inlet temperature differences, and delta T2 shows the outlet temperature differences. Okay, so delta T is nothing but so hot fluid temperature minus cold fluid temperature. Okay, we'll see. And initially we'll take the small elemental area. So we'll derive the rate of heat transfer for the small elemental area. So okay, so before going to that, we have to assume some, have to consider some assumptions also, because have to take some assumptions. Here first, you know that U is the overall heat transfer coefficient. So U is uniform throughout the heat exchanger, because so U value, variation of the U is not considered here. Okay, we will take it as a uniform parameter throughout the heat exchanger. And the potential and kinetic energies. So changes of the potential and kinetic energies are negligible also. We are not considering the changing of energies. Okay. Next, specific heats of the cold fluid and the specific heat of the hot fluid and specific heat of the cold fluid. So these are also, we are taking constant values. Okay. So these are not changing. So these are not variable parameters here. So fourth one is the heat exchanger takes place only two fluids only we are considering. So in heat exchanger, just like heat is transferred from the hot fluid to cold fluid. So that is the assumptions. So temperatures of the both fluids are constants. So inlet temperature of the hot fluid and inlet temperature of the cold fluid. So these are the just like fixed parameters. These are not variable parameters. Just like, so once the value of inlet parameter, inlet to temperature of the hot fluid is given, that is fixed for the for complete heat exchanger. So temperatures of both fluids are constants over the given cross section. So these values, inlet temperatures or outlet temperature, does not vary with respect to cross sections. So these are the assumptions to derive this formula, LMTD formula for the heat exchanger, parallel fluid exchanger. Okay. So first we will see the small elemental area for this one. Okay. So the heat transfer between the hot and cold fluid of the for the small elemental area. Okay. So the length of the small elemental area is equal to dx. We know that. So then dq formula, dq is equal to u dA. Initially q is equal to, you know the formula, ua into delta TLM. For the small elemental area, it means small dq is equal to UdA into delta T. You know that this delta T is nothing but hot fluid temperature minus cold fluid temperature. Okay. So here you can see these values. Just like this is the same diagram. You know that. Okay. So you know that delta T is equal to TH minus TC. So you know the energy balance equations for the small elemental area. You have to consider that one. So you know that Q is equal to that formula. Q is equal to mHCH into delta TH. So so temperatures of the hot fluid. So okay, for the small elemental area. For the small elemental area, here also small dq is equal to, so minus mH and ch into dTH. So this dTH, so hot fluid temperature differences, you know that hot fluid inlet and hot fluid outlet. So you can rewrite like this one, mh ch is nothing but capital ch, you know that, specific energy. Okay. So similarly, just like small dq is equal to, with respect to cold fluid, mccc into dtc. Okay. So mccc is nothing but capital cc, specific energy, into dtc. Okay. So here just like we are observing the just for the energy equation of the small element area. Here we are observing the minus. Here there is no minus. You know that because here just like for the hot fluid temperature, if you observe the graph of this one, the hot fluid temperature is, the graph is decreasing order. So enthalpy is decreasing order. For the cold fluid, so heat is gaining, just like graph is in increasing order. So for this one, just like for the hot fluid, you can take the minus for the small elemental area in case of this one. So in case of cold fluid, see, it is increasing order, no need to take off the minus here. So you know that the delta T is equal to uh, hot fluid temperature minus cold fluid temperature. If you apply this small derivative, so derivative of delta T is equal to dTh and dTc. Okay. So here dTh, you know that value, dTc also you know that. So dTh is equal to, here dTh is equal to so dq by minus capital ch, dTc here just like dTc is equal to dq by capital cc. So these are the values. You can substitute these values in case of, in place of the dTh and dTc. So this is the values. So dTh is equal to minus dq by ch. You can substitute that value. So minus dq by ch, minus is also here. So then dTc is equal to dq by cc. Okay. So minus dq by cc. Here in both cases, just like derivative of delta T is equal to, here just like minus dq is the common term, you can take minus dq as the common term, then 1 by ch plus 1 by cc, this is the value. Just like you will see. So this is the formula. So derivative of delta T is equal to minus dq into 1 by ch plus 1 by cc. You know that the dq formula, you know that dq is equal to u dA into delta T dt. So temperature difference. Okay. So you can substitute this formula here, just like if you substitute this formula, minus u dA into dt into 1 by ch plus 1 by cc. Okay. So here you can turn this dt in temperature side, then the formula is like this one. So derivative of delta T by dt is equal to minus minus of 1 by ch plus 1 by cc. These are the constant values. So derivative of a. So then, so this is the formula for the small elemental area. If you integrate this one with respect to limits, boundaries, then we will get the final formula for the entire heat exchanger. Then integrate this one. Integrate just like so. Integrate here. We will see in graph already in the graph. So this is the hot fluid inlet. So this one is the cold fluid inlet. So it is gradually increases, gradually decreases. So this is the hot fluid outlet. This is the cold fluid outlet. Okay. So you know that this is the delta T1. This is the delta T2. Okay. So here just like ranging. So limit ranging for the temperature is the delta T1 to delta T2. Okay. So you can take. So take the delta T1 to delta T2. So these are the limiting ranges. Derivative of delta T by delta T. So it shows the entire heat exchanger. Entire heat exchanger. Okay. So similarly, minus u into 1 by ch plus 1 by cc. So if you take, this is the session 1 and session 2. So integral 1 to 2 into dA. So here just like area is uniform, does not change with respect to the just like point 1 to point 2. So here area same, uniform area. Just like integral of dA, you can take, that is the area A. Okay. So integral of derivative of delta t by delta t is equal to log delta t. You can see the formula. So ln delta t, if we apply the limits, delta ln delta t2 by delta t1 minus u. So derivative of dA is equal to area. Okay. So you can write like this one. So ln delta t2 by delta t1 is equal to minus ua into 1 by ch plus 1 by cc. This is the formula. So next to, the energy formulas for the these are the energy formulas according to thermodynamics. The formulas. Rate of heat transfer is equal to mHch into temperature dTh, temperature differences, hot fluid temperature minus cold fluid temperature. Hot fluid inlet minus hot fluid outlet. Okay. You can read it like this one, capital CH into temperature of hot fluid inlet minus temperature of the cold fluid outlet. So here just like we, the 1 by CH. So in place of 1 by CH, just like how to derive this formula. So here CH is there, then you can shift this term to left side, then 1 by CH is equal to, so THA minus TH naught by Q, you will get that. So similar manner, just for the cold fluid, the formula for the cold fluid, Q is equal to MCCC into cold fluid outlet minus cold fluid inlet. So you know that MCCC is nothing but capital CH, specific energy, just 1 by CH is equal to TC naught minus TCA by Q. Then you can substitute these values in this formula. So in this equation, then we will get the, so this is the values. So you know that this is formula, same formula, ln delta T2 by delta T1 is equal to minus UA into 1 by CH plus 1 by CC. So you know the 1 by CH and 1 by CC values. This is the 1 by CH value, this one is the 1 by CC value. Substitute these values in this place, in this equation, then you will get this this equation. So ln delta T2 by delta T1 is equal to minus UA by Q. So because in both conditions Q is common, so you can take common Q. So then THA minus TH naught plus TC naught minus TCA. So we can rearrange these temperatures like this one, you can see. So ln delta T2 by delta T1 is equal to minus UA by Q. So THA minus TCA. So just we are writing first. So cold fluid inlet minus of TH naught minus TC naught. So you can rearrange that one. So you know that this is nothing but according to temperature graph. So THA minus TC naught TCA is nothing but delta T1. Similarly, so hot fluid outlet minus cold fluid outlet, that is nothing but delta T2. Okay. So you can substitute these values in this formula, just like we will get this one. Okay. So UA by Q is equal to, this is nothing but delta T1, this is nothing but delta T2 according to the graph of parallel fluid exchanger. Okay, you know that this one here minus is there, we can shift this minus into bracket, then UA by Q is equal to, it will comes first and it will goes to last. So because of minus, so plus will be minus, minus will be plus, then this is the delta T2 minus delta T1. Then you can rewrite like this, and you require the just like rate of heat transfer, then Q is equal to, the formula is equal to UA into delta T2 minus delta T1 by ln delta T2 by delta T1. Otherwise we can rewrite like this one. So already you know that UA into delta T LM. So this delta T LM is nothing but, this delta T LM is nothing but delta T2 minus delta T1 by ln delta T2 by delta T1. Otherwise, you can rewrite like this one. Delta TLM is nothing but delta T1 minus delta T2 divided by ln. Here also delta T1 by delta T2. You can write like this one. So this is the logarithmic mean temperature difference for the which one, parallel fluid exchanger. So this is the final formula. Based upon this formula, you can find out the rate of heat transfer for the heat exchangers. Okay. So you know that delta T1 is the for the parallel fluid is nothing but hot fluid temperature inlet minus cold fluid inlet. Delta T2 is equal to hot fluid outlet minus cold fluid outlet. Okay. So this is for the parallel fluid exchanger. Okay. So in this way, just like you can find out the rate of heat transfer in the parallel fluid exchanger. Okay. Now we'll see the rate of how to find the delta TLM for the counter fluid exchanger. Okay. We already derived this formula or solved this delta TLM formula for the parallel fluid exchanger. Now we'll see the how to derive this delta TLM. So logarithmic mean temperature difference for the counter fluid exchanger. So you know that three types of heat exchangers are very important. That one is the parallel fluid exchanger. Next one is the counter fluid exchanger. Okay. So we'll see that one also. So you know that counter fluid exchanger. I want to repeat that one. So in last class I already explained that one. So here also you know that heat exchanger, heat is transferred between the two fluids. One is the hot fluid, another one is the cold fluid. Okay. So this is the inlet pipe. So this one is the outlet pipe envelope. Okay. So here hot fluid is entering at a B. So left to right. So hot fluid inlet and a hot fluid outlet. Okay. Here just like, but cold fluid enters at A. So this is the cold fluid inlet. Okay. So it flows in opposite direction to the hot fluid, like this one. You know that already discussed in previous class also. Okay. So this one is the cold fluid outlet. Okay. So in counter flow, at one end we will see the hot fluid inlet and cold fluid outlet. Another end, cold fluid inlet and hot fluid outlet. Okay. So just small difference between the cold fluid parallel fluid exchanger and counter fluid exchanger. So you know that this is the parallel fluid exchanger temperature graph. So temperature distribution graph. So this is for the counter fluid exchanger temperature distribution graph. Okay. So hot fluid inlet. So hot fluid enters, hot fluid outlet. So here hot fluid is in decreasing order. Okay. And cold fluid enters at B section. Here it cold fluid enters. So the temperature of the cold fluid gradually increases. So like this one. This one is the cold fluid out. Okay. So in this case, just like so hot fluid and cold fluid is decreasing order. If you observe this graph, these are the decreasing order. For this one, you will take that minus for the small elemental area. For this one, rate of heat transfer of small elemental area. We'll see that one also. Now we'll see. So derivation of LMTD for the counter fluid exchanger. So you have to remember, so what is delta T1 and delta T2 for the counter fluid exchanger. You know that this is the parallel fluid exchanger. Parallel fluid exchanger, delta T1 is equal to hot fluid inlet minus cold fluid inlet. But for the counter fluid exchanger, delta T1 is equal to hot fluid inlet minus cold fluid outlet. Okay. So similarly, delta T2 is equal to hot fluid outlet minus cold fluid inlet. So this is the difference, main difference between the parallel flow and the counter fluid exchanger. Okay, now we'll go for the derivation. Initially, we'll take the small elemental area, so similar to what was done in parallel fluid exchanger, just same method you have to follow that one. So here we are taking this small elemental area. You know that area of this small elemental area is equal to dA. Okay, so we'll derive that formula. So same here also. So graph for the counter fluid exchanger, just like delta T1 hot fluid inlet minus cold fluid outlet, delta T2 hot fluid outlet minus cold fluid inlet. Both are in decreasing order. Okay, so you have to remember this one. Same assumptions we have to take this one here also. Oral heat transfer coefficient is uniform. Potential energies or kinetic energies are negligible. Specific heats CH and CC are constant values. Okay, heat exchange takes place only between two fluids. We have to consider this one. So temperatures inlet and outlet of cold fluid, inlet and outlet of hot fluid are the same at any cross section. Okay. So initially the rate of heat transfer between the hot and cold fluid for the small elemental area. Okay, length of this small elemental area is equal to dx, same formula. So then dq is equal to small, so u dA into delta t. Okay, so it means u dA into delta t is equal to hot fluid temperature minus cold fluid temperature for the small elemental area. Okay. So you know that energy balances equations for the small elemental area here. So small dq is equal to minus mhch into dth. Okay, so you can rewrite like this one. mhch is nothing but capital ch. So here minus, because in both cases temperature profile is like this one, decreasing order for the small elemental area. Okay, so here just like we have to take this minus for the both the fluids. So here just like minus capital ch into dth. So here cold fluid minus cc into dtc. This is dtc. Okay. So then you know that formula delta t is nothing but dth th minus tc. So derivative of delta t is equal to dth minus dtc. Okay, you know that dth is equal to this one, dtc is equal to this one. So here just like dth is equal to dq by minus ch, dtc is equal to dq by minus cc. Okay, so substitute these values in this here. So it means the derivative of delta t is equal to, so in both cases here also minus dq by ch, minus of minus plus dq by cc. In both cases minus you can common, minus dq can take common. So 1 by ch, so minus of minus minus, so 1 by cc. This is the formula like this one here. Just so derivative of delta t is equal to dq into minus 1 by ch. You can write it, otherwise you can take minus common. So 1 by ch minus 1 by cc. You know the dq, you know the formula of dq is equal to, so u dA into delta t dt. Okay, dt or delta t, both are same. Okay, so you can write like this one. So this dq is equal to, you know the formula. So then the formula is like this one. Okay, so you can turn this dt this side and dA. So this is the just like equation for this small elemental area. Then you can integrate this one with respect to limits. You will get the entire equation for the total heat exchanger. You know the limits. So already you know the limits. So this is the temperatures of hot fluid. This is the temperature of the cold fluid. This is the hot fluid inlet, hot fluid outlet. So cold fluid inlet and the cold fluid outlet. Okay, so this one is the delta T1, This is the delta T2. So ranges 1 to 2 means delta T1 to delta T2. So here you can take the ranges delta T1 to delta T2. These are the limits. So integral dA. So it is the 1 to 2. 1 to 2. See here, just like the cross-sectional area of the heat exchanger for the 1 to 2 does not changes. It means area does not change with respect to points. So it is uniform. Then integral of dA is nothing but A. Okay. So just like you can write like this one. If you integral this with respect to limits. So this is the. So then finally you will get the ln delta T2 by delta T1 is equal to minus UA into 1 by CH minus 1 by CC. Okay. So integral of dA is equal to A. This is the log delta T. Then if you apply the limits, you will get this one. Okay. Now you know that energy equations for the so rate of heat transfer. So according to thermodynamics, Q is equal to mHch into temperature difference of hot fluid inlet minus hot fluid outlet. Okay. mHch is nothing but capital CH into hot fluid inlet minus hot fluid outlet. Similarly, so Q is equal to for this cold fluid mCC into cold fluid outlet minus cold fluid inlet. Okay. So you know that mCC nothing but capital CC into TC naught minus TC. So these are the formulas. Okay. So then you can rewrite like this one. These formulas here, just like here you can see. So these are the energy equations. You know that. So 1 by CH is equal to this formula, complete formula. Then 1 by CH is equal to so hot fluid temperature differences by Q. 1 by CC is equal to cold fluid temperature differences by Q. Okay. So substitute these values 1 by CH value and 1 by CC value in the previous one. What is it in this one? Okay. If you substitute this one, you will get this one. Okay. So substitute these values in this equation. Then ln delta T2 by delta T1 is equal to minus UA by Q into, so 1 by CH value is nothing but this one. 1 by CC value is nothing but this one. If you substitute this one, you will get it. Then you can rearrange this one because according to delta T1 and delta T2 of the counterflow, you know that values. So delta T1 is nothing but hot fluid inlet to cool fluid outlet. Okay. So first you have to rearrange this one, and next you have to rearrange between these two parameters. Okay. So based upon these two parameters, we will get to delta T1. Based upon these two parameters, we will get to delta T2. Okay. So we can rearrange like this one here. Okay. Like this one. So THI minus TC naught. So take minus common. TH naught minus TC. Okay. You know that this is the delta T1. This is the delta T2. Is it? Okay. So then the formula is like this one. So ln delta T2 by delta T1 is equal to minus UA by Q into delta T1 minus delta T2. You know there is a minus. Okay. So based upon this minus, if you send this minus into bracket, so the formulas will be like this one. UA by Q into delta T2 minus delta T1. Then Q is equal to UA into delta T2 minus delta T1 by ln delta T2 by delta T1. This is the formula. You can see here like this. So this is the final formula for the rate of heat transfer. You can rewrite like this one, like Q is equal to UA into delta TLM. Same formula for the parallel fluid exchanger also. Okay. Here delta TLM. So logarithmic mean temperature for the hot fluid and cold fluid. So delta TLM is equal to same formula, delta T2 minus delta T1 by ln delta T2 by delta T1. Okay. So same formula for the parallel flow, same formula for the counter flow. But delta T1 and delta T2 values will be changed. So we know that delta T1 is in parallel flow is equal to, so inlet temperatures of hot fluid and cold fluid, but counter flow delta T1 is equal to hot fluid inlet minus cold fluid outlet. So delta T2 is equal to hot fluid outlet minus cold fluid inlet. You know this formula. So just like so, finally you can find out the rate of heat transfer for the counter fluid exchanger. Same formula, UA is equal to delta T LM. So similarly, rate of heat transfer in the parallel fluid exchanger. Okay. So only the difference is equal to delta T1 and delta T2 values. So limits of that one. Okay. So in this way, we can find out rate of heat transfer in parallel flow and counter fluid exchanger based upon the logarithmic means. Okay. So this is different from the previous formulas. You know that formulas of conduction and convection. So convection formula, you know that HA into delta T. So temperature differences only. So little bit difference. Here we will see the delta TLM, logarithmic mean temperature difference. So that is the difference for the heat exchangers. Okay. So finally, these are LMTD method for the parallel fluid exchanger and counter fluid exchanger. In next class we will see some numericals based upon the LMTD method. I want to explain those numericals. So thank you for this listening class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.